Howdy, welcome back to my lecture series of introductory astronomy, specifically for my class ASTR 103 Astronomy, spring of 2022. This is lecture 8, and what we're going to be discussing today are planetary systems, their birth and architecture. In other words, I am going to detail the characteristics of our own solar system, and then I will talk about how that then I will talk about exoplanets and how that has informed our understanding of how solar systems are formed, and then I will talk about the basic mechanics of solar system formation. Hey, I remember to do that. So, the first question is, what is in our solar system? In a very gross way, we have the Sun and 8 planets. So these are the major bodies within the solar system. Now, I'm going to caveat, or it's going to come with a major caveat. I am contractually obligated to teach you that Pluto is not a planet. I fundamentally disagree with that assessment on a physical basis, and maybe I will do a separate video where I go into depth of why I believe Pluto is a planet, and it goes beyond the NASA chief's rationale of, well, that's what I was taught. There is, I believe, significant physical reasons for why downgrading Pluto was a mistake. Now, with that being said, we have 8 planets, and they can be subcategorized, roughly speaking, by their compositions. We have 4 terrestrial planets, which are rocky in nature. We have 2 gas giants, which are Jupiter and Saturn. And then we have, which are primarily hydrogen and helium in composition. Then we have ice giants of Uranus and Neptune. They are referred to ice giants not because they are predominantly icy. They are still predominantly made up of hydrogen and helium, but they have a much larger or much higher concentration of ices in their upper atmosphere, particularly in comparison to Jupiter and Saturn. So what is a planet? Now, again, this is a sore point for me, but anyway, the definition of a planet was accepted by the IAU. A planet, the first definition, or the first criterion of what a planet is a body orbiting a star. And as an aside, that's not actually what the IAU said. The IAU's definition is a planet, or is a body orbiting the sun. It's one of the reasons why I disagree with these definitions, because one, it's not inclusive. But anyway, I digress. So let's back up. The definition of planet has 3 characteristics, or 3 criteria. A planet is a body that's orbiting around a star, a body that is massive enough that under its own gravity, it pulls itself into a spherical shape without being massive enough to ignite stellar fusion. And then 3 is that the planet needs to be a bully, that it has cleared out all smaller objects from the neighborhood of its orbit. Our solar system is more than just these 8 planets. There are quite a number of smaller bodies within our solar system. These include dwarf planets, asteroids, comets, trans-Neptunian objects, things of this nature. And I will go over these in a little bit more detail later on. The 2 things that you can see here are the 2 largest dwarf planets, Ceres at the top and Pluto at the bottom. And as I said, there are other objects, planets, or excuse me, comets, asteroids, meteoroids, and trans-Neptunian objects. So why do we care? Why do we bother classifying things at all? Because that informs our understanding of how they got there in the first place. By looking at these objects and placing them in certain categories is a technique we refer to as comparative planetology. So we look at these objects, and we see whether or not there are any commonalities between various bodies in the solar system, and whether or not there are differences between various bodies. So, for example, one example is we have 4 rocky planets and 4 ultimately gas planets made primarily of gas. The rocky planets are close to the sun, and the gas giants are away from the sun. So any theory as to how the solar system came into being has to account for those rocky planets being being close to the sun, and those 4 gas giants being away from the sun. So this classification allows us to, or provides benchmarks and constraints to any theory that we come up with in terms of how a solar system is created and ultimately how it's going to evolve with time. So the regions of the solar system, there are roughly 4 regions. There is the inner planets, plus the asteroid belt. There is the outer planets, the gas giants, ice giants. There is the Kuiper belt and scattered disk. This is primarily composed of comets and dwarf planets, and these are things that are outside the orbit of Neptune. The dominating characteristic of Kuiper belt and the Kuiper belt and scattered disk, besides the composition of the objects within it, is that the Kuiper belt is fairly narrow, it's fairly thin in comparison to, say, the Oort cloud. The Kuiper belt is still disc-like in shape. It's still fairly constrained to the ecliptic. Then beyond that, we have the Oort cloud, which is a large spherical region of cometary bodies, where occasionally one of those bodies gets gravitationally thrown into the inner part of the solar system. And so we study those objects, and hence why we know that the Oort cloud exists. So when we look at the size of our solar system, the inner part of the solar system is roughly around 7 AU, out to about across, out to about the distance of the asteroid belt. Out to the distance of the Kuiper belt, you're talking about 100 AU, and then the Oort cloud is encompassing everything of 100,000 AU or less. So the Oort cloud is by far the largest structure in the solar system, and that is an estimate. The Oort cloud is, if I'm to be honest, poorly understood. It is because the objects are so small and so far away. They are very, very hard to observe, and so we are basing a lot of what we know of the Oort cloud on the models that we've used to create the solar system, and create it in such a way that that model evolves into what we see from first principles. So the properties of these planets is as such. So we have the inner planets, or the terrestrial planets, gas giants and ice giants. Now, if we look at the relative sizes, the terrestrial planets are fairly small. The gas giants are very large, typically on the order of about 100 times the mass or the size of the Earth. And then you have the ice giants, which are kind of in the middle. They're still fairly large in respect to the terrestrial planets, but they're not nearly as large as the gas giants. They're only maybe a dozen or a score a couple dozen or 20 times the mass of the Earth. Composition, as I said, the terrestrial planets primarily made up of rock and metal. Gas giants, primarily hydrogen, helium, with a few heavier elements in their abundances, primarily hydrocarbons like ammonia, methane, so forth. Ice giants, I know it says mostly ices. That's kind of that's wrong. The ice giants, as I said, are primarily hydrogen and helium. They are called ice giants because they have a much higher concentration of ice crystals or icy material in their upper atmosphere than the gas giants. And they have a larger concentration of hydrocarbons as well. I should probably change this slide. When you look at the orbital distances, the terrestrial planets, as noted, are much closer to the Sun than the other planets, less than 2 AU. Gas giants and ice giants. The gas giants are relatively medium distance, and then the ice giants are the farthest away. In terms of orbital characteristics, all of them are roughly the same. All of them have roughly the same orbital characteristics, and by that I mean that the eccentricities, or circularization, or ellipticity, depending on how you want to make up crazy names for it, depending on how you want to say that, the eccentricities are close to zero, meaning that most of the orbits are close to circular. They're all fairly along the same line. If you remember, the ecliptic plane is the plane going through the solar system as defined by the Earth's orbit. The inclinations, or degree off of that plane, is modest, maybe 5, maybe 10 degrees off of that. So they're fairly well constrained into what we refer to as a disk. Now, rotational direction, again, is pretty much the same for all the planets. This slide notably says Venus, but there is also Uranus as well. Venus is weird because it does not rotate. It rotates essentially backwards. It has retrograde rotation. So as the sun rotates, if by looking down on the sun from the north, you will notice the sun rotates counterclockwise. All of the other planets, except for Uranus and Neptune, except for Venus and Uranus, also rotate counterclockwise. And incidentally, the planets are all revolving around the sun in a counterclockwise direction. That is fairly critical to our understanding of how the solar system came into being. Now, Venus is, like I said, completely backwards. It rotates clockwise when viewed from the north. And Uranus literally rolls through the solar system. Its inclination angle is a little bit more than 90 degrees, which means if this is 0, then this is Uranus's orbit. So it basically rolls as it goes through. In both cases, we suspect that the reason why the rotation axes are different than the rest of the solar system, or the rest of the major planets, is that they were struck by something fairly large in the formative period of their formation. I guess that might be redundant. In the early parts of their formation, they were struck by a large object, which basically flipped the planetoid around. Then finally we get to cores, magnetic fields, satellites, rings, and rotation rates. For terrestrial planets, their cores are mostly iron and partially molten. The Earth, for example, has a solid and liquid core, which allows for it to be geologically active, which in turn allows for the magnetic field of the Earth to be fairly strong or moderate. As the planets age, they become less geologically active, and so their magnetic fields get much weaker. So in comparison, you have Earth's magnetic field, which is moderate. Venus and Mars do not have as strong a magnetic field, and then you're left with Mercury, which has a very, very weak, what's the word I'm looking for? Not primordial, but it has a very, very weak, very, very weak baked-in magnetic field. None of the inner planets have rings, and for the most part, they shouldn't have moons. Mars has 2 moons, otherwise known as the potato moons, but those weren't formed with Mars. Those are captured asteroids from the asteroid belt. The Earth's moon, and I'll talk more about that later on, the Earth's moon is really a cataclysmic event. We believe that a Mars-sized object smacked into the Earth at a very early stage of its creation or its formation, and blew off material that then coalesced into the moon. That is a fairly rare event. So we do not expect this. If we were to look for terrestrial planets out in the universe, we would not expect this to be very common among terrestrial planets. And so therefore it's not a defining characteristic of them. Typically speaking, they should not have satellites or rings. And they rotate fairly slowly, on the order of days or months in the terms of Mercury. Gas giants, we suspect, again, we don't, through modeling, we suspect that gas giants have a small rocky core, as do ice giants. Magnetic fields are very strong, or at least much stronger than the magnetic fields of the inner planets. With the gas giants, those magnetic fields appear to be what we really expect. They are fairly much in line with the rotation axis of the worlds. Ice giants, on the other hand, are not, and they are off-center. So, given our understanding of how these magnetic fields are generated, ice giants are a bit weird. All of these, both the gas giants and the ice giants, have ring systems. Obviously, Saturn's is the most robust, but all of them do. We have discovered that through satellite observations of these worlds. And they have many moons. They have dozens upon dozens of moons. Most of them are small, potato-y type moons. These are moons that are larger than asteroids, but not spherical under their own mass. Jupiter really only has 4 that fall into that category. Saturn only really has 1, and Neptune really only has 1 as well. All the rest of the moons are fairly minor, but there are larger. There are a large number of them. In terms of the rotation periods of both gas giants and ice giants, we're talking very relatively fast, on the order of half a day or a little bit more than that. Basically, days, if not less. So they are rotating very, very quickly. Then we have asteroids, comets, meteoroids, and trans-Neptunian objects. Oh my. These are bodies that are have various compositions. They're located in various areas. And so when we compare, say, for example, asteroids and comets, asteroids are primarily rock and metal. Again, they are located primarily in the asteroid belt, although that is not an exclusive zone. They typically have low eccentricity and inclination and are in stable orbits. And their size can be down from 1 meter to 1,000 kilometers. Comets, on the other hand, have a much smaller size range, from about 100 meters to 50 kilometers. They're primarily made up of ice that is frozen over a rocky core, with metal, with rock kind of intermixed with the ice. We basically refer to comets as dirty snowballs at this point. Their locations are in the outer parts of the solar system, either in the Kuiper Belt or beyond. Their orbits tend to be, Kuiper Belt comets, or short period comets as they're also known, their eccentricities are mostly circular, although there are some obvious exceptions. and their inclinations are typically within the plane of the solar system. There again are certain exceptions. The Oort cloud, on the other hand, is a free-for-all. The eccentricities range from nearly circular all the way up to highly eccentric, and they are all over the place. They literally make a sphere, so the inclinations run the full gamut of values. Asteroids are believed to be, derisively speaking, asteroids, comets, yada yada. These are referred to as solar system debris because we believe that these objects are the leftover remnants of planetary formation. We'll talk later on. We will talk about the fact that when the solar system first came into being, when we look at the large, basically rocky elements of it, these started forming. They started from dust grains and then formed into larger and larger planetesimals, and they would coalesce. And the planets, they would smack each other. They would collide, and depending on the dynamics of that collision, they would either fuse together and make a larger object, or they would break apart. And so, the planets that we see today were the winners. They managed to stay together as large bodies, grow to fairly large size, and in the case of the outer planets, obtain a very significant atmosphere. Asteroids are essentially the leftover remains. These are the pieces of the solar system that never found larger homes. Either they broke off from larger planetesimals, or they are just the remnants of just the planetesimal that got broken up. Or they may not have. They may have coalesced into the shape that they got, and then just never got any bigger because of reasons. Because either there were not enough material near them, they formed late, things of that nature. So yeah, they are solar system debris, and that also includes asteroids, but it also includes comets. When we talk about asteroids, we have essentially two major types. We have the C types, which are stony in variety and typically have relatively high concentrations of carbon. And then we have S types, which are also rocky, but they're made up of silicon rocks. Now there is a third type, which are iron, basically. These are, as you might expect, bodies that are primarily composed of iron. And depending on their compositions, we know that we can essentially determine where they were in terms of solar system evolution. So, for example, there is this process called differentiation. So when you have a large ball of liquid hot magma, that ball of magma can be composed of many different elements. Aluminum, carbon, iron, nickel, that sort of thing. And they're going to be fairly homogeneously distributed in that initial mass. But over time, because of gravity's influence, more dense objects are going to fall into the center of the body. And so your irons and your nickels are going to be more centrally located, whereas your aluminums and carbons and silicates are going to be near the top. And this is what we refer to as differentiation. C-type asteroids are not strongly differentiated, which means either they were the top layers of a large planetesimal that got blown off, or they were just not. They were not built into planetesimals. They were not large enough for differentiation to become a major factor. S-type asteroids do seem to be more differentiated, and so they were probably deeper down in the planet, more like, say, the mantle region. So C-type asteroids were more crustal. The S-type asteroids are more mantly. And then when we go to M-type, or metal types, iron types, those are the cores of planetesimal. So you had a planetesimal that was fairly fully differentiated, and it broke apart for whatever reason. The the C types were near the top, the S types were near the middle, and then the irons were near the center. Asteroids and water. So water is, incidentally enough, water is fairly ubiquitous in the solar system. Now, liquid water is not. As far as we know, liquid water on the surface of a world is only found on the Earth. However, we have found ice, water ice, on pretty much every major surface of a rocky or solid body. This is an example of the Dwarf planet Ceres, which is located in the asteroid belt. There is a liquid or ice deposit in the center of a large comet. And so, one of the things that we believe is that the water content of the solar system was put there by comets. So essentially you had water froze into ice in the outer parts of the solar system, and then those objects were on elliptical paths and came into the inner part of the solar system, smashed into stuff, and deposited the ice there. And depending on the conditions that formed the planet, particularly with the Earth, it was conducive to actually melting that water and forming oceans. Now, that is the most accepted or most widely accepted explanation for why there is water, particularly on the Earth. However, there are problems with that theory, primarily the composition of the water, hard water versus normal water. And so there are some ideas coming or being developed now that actually claim that a good chunk of the water that we see on the Earth, for example, was actually homebound. It was formed with the Earth itself. But I digress. Now there are two other major regions of asteroids. There are the Trojan asteroids, which are, or Trojan and Greek asteroids, depending on who you talk to. These are asteroids located in a strange-ish or a region which we refer to as Lagrange points. These are points in surrounding the orbit of a planet where, due to the gravitational effects of Jupiter or the planet and the sun, these are points of stability, as it were. If an object falls into this region, it's going to essentially be held there by the mutual gravity of the planet and the sun. And so we have at Lagrange points 4 and 5, which are before and after the planet. We have for Jupiter, because it's large enough, has collected some of those asteroids from the main belt and deposited them in those Lagrange points. Now, if you're more classically inclined, one of the, I believe it's usually the one in front is the Trojans, and the one in the back are Greeks. The other group of asteroids, which is more of interest or concern to just ordinary folks, and these are called NEOs, or near-Earth objects, and a subsection of those are Earth-crossing asteroids. These are asteroids whose orbits place them very close to the passing by the Earth, and would constitute potential collisions, even to the point of creating another mass extinction, like happened 65 million years ago, wiping out the dinosaurs. And so NASA has been very invested in finding these asteroids and developing techniques to deal with them if they prove to be on a collision course. The reason why they are hard to find is their albedos are low, meaning that their reflectivity is not very high. Albedo is the percentage of reflected light from incident light. So a mirror, for example, has a very, very high albedo. Iron, for example, has a very, very low albedo. It doesn't reflect a lot of the light that comes off of it. And so because of the fact that the albedos are low, because they are so small objects to begin with, they are not overly visible, and so it's very difficult to find these objects before they become dangerous. But, as I said, NASA's on it. The Europeans are on it, so sleep tight. Then we have comets. Now, there are three major components to a comet. There is the nucleus, which is ultimately the heart of the comet, is the main constituent of the comet. It's the solid body. It's composed of, again, rock and ice. And if it's far enough away from, if the comet is far enough away from the sun, that's all you have. You basically just have a chunk of ice and rock floating through space. But as the comet, if the comet is on a elliptical path, then it will pass closer to the sun, and as it does so, it'll heat up. And as it heats up, the ice will sublimate. That means going from a solid state to a gaseous state. It'll skip over the liquid part. And when it sublimates, that gas is still going to be gravitationally trapped to the nucleus. And it forms what we refer to as a coma. This just basically cloud of typically water vapor is the primary constituent of water vapor surrounding the nucleus. And then as the comet gets closer and closer to the sun, more of that coma gets larger and produces a jet or a tail. Now, I'll get into the tail in a moment. But you have, as I said before, you have two classes of comets. You have the short period of comets. They, depending on who you talk to, that is classified as either comets with orbital periods of 100 or maybe even 200 years or less. These are found within the Kuiper Belt and the scattered disks, and they have lower eccentricities and lower inclinations as compared to long period of comets. Their eccentricities are still high, because that's what brings them into the inner part of the solar system, but they are lower in relation, again, to longer period comets. Longer period comets have orbits obviously longer than 200 years, and some of them are thousands to millions of years. Most of them are thousands to millions of years. We believe that these originate in the Oort cloud and, again, have the highest inclinations and eccentricities. So if you look at the plane of the galaxy, if you look at the plane of the solar system, you have the sun, you have planets going around in this way. So these short period comets are coming along basically in line with that disk. They're coming around, they're orbiting close to the sun, and they're shooting back out. As illustrated, long period comets tend to not do that. They come in at a very steep angle, and we see them once, or at least within our lifetime, we definitely only see them once. And they go whizzing away back to the outer regions, cold, dark regions of space. Now, that jet or tail that I talked about, which is essentially the coma being blown backwards, comes in two varieties. You have a dust tail and an ion tail, best displayed when the comet Hale-Bopp came by. The dust tail, imaginatively enough, is composed of dust, silicate grains. The ion tail is imaginatively is composed of ions. Ions are electrically positive or negative particles, either electrons sitting out by themselves or protons, or the nucleus of an atom sitting out by themselves. And the reason why they're not in the same line, why you can see them differentiated the way they do, is because they are blown off the nucleus or blown out from the coma in different ways. The dust tail is literally pushed by sunlight. Light does exude a pressure on objects. It is just a very, very tiny amount of pressure. However, we're talking about really, really tiny dust particles that have very, very low mass. So even a tiny amount of force can accelerate these tiny masses out to extreme distances like you see in these dust tails. And the dust tail is canonically what you expect when you draw, if you're a child and drawing a comet, you draw that tail, that curvy tail, that's what you see, or that's what the dust tail is. The ion tail goes straight out. You can draw essentially a straight line through the tail, through the nucleus, right at the sun. And the ion tail is produced because of the magnetic interactions between the solar wind and the ions in the tail. Basically, the ions that get created when the gas sublimates from the coma and creates the coma. We'll talk more about what the solar wind is later when we talk about the sun, but essentially it is a magnetic phenomenon where you have ions from the sun getting paired with ions from the comet, and they get blown off in a radial direction straight away from the sun. What's fun is that the two tails do not, in fact, always follow the comet. Typically, when we think of comets, we think of the core or the nucleus in front, and the tail is behind it, and it's traveling as such. But that's, like I said, not always the case. That is only the case on the incoming flight, because in both cases, it's the sun that is blowing away blowing the tail outward. So as the comet comes around the sun and leaves, then the tails actually precede the comet. And some of these comets can have tails that are AU in size. They can be immense, depending on how much sublimation is occurring on or essentially how big the nucleus of these comets actually are. Comet Hyakutake, which has a very special place in my heart, it was close enough that tail was degrees in size. It was numbers of moons in size, like about 3-4 moons across, and you could see it with a reasonable sized telescope. I've already really talked about this. This is basically the idea of water on Earth being placed there by higher eccentricity orbits, or highly elliptical orbits of asteroids and comets. Next we have meteoroids. And at some point, when I get really bored, I'm going to find out who was the ingenious person who came up with this nomenclature. Because as far as I know, it is the only time that we have 3 names for the same object. Meteoroids are essentially really tiny asteroids. They are rocky bodies that are a meteor in size or less, all the way down to a grain of sand. They're always rocky, they're always metallic. So it's a meteoroid. This is the same object, mind you. It's a meteoroid if it's running through space. Once it hits the atmosphere of anything, the Earth for example, then it's a meteor. So when we look up and we see meteor shower, that's the meteor, the previous meteoroid slamming into the Earth's atmosphere and essentially creating a fiery streak across the sky. If it were to survive this burning up in the atmosphere, if there's something left, then that remnant, once it hits the ground, is referred to it as a meteorite. So you have meteoroids in space, meteors in atmospheres, meteorites on ground. Meteorites are, because of their compositions and the fact that they were on fire, are dark in color. And so, ironically enough, the easiest place to find meteorites is actually Antarctica, because, well, it's all white there. It's pretty much just ice. So it's actually fairly easy to find meteorites there. You can actually, I don't know how much it costs, but you can actually pay to go on tours, meteorite hunting tours. You can go down to Antarctica, and they allow you to wander around a particular patch of Antarctica, and you can pick up as many meteorites as you can find. Meteorites, Again, they're pretty much the same, or they have classifications similar to asteroids. You have stonies, or stone objects, and then you have, which you can see on the left, and then you have iron and nickel meteorites on the right. And as you would expect, iron meteorites are hefty. A colleague of mine, she has one which is about a foot and a half in size, foot and a half in diameter, as it were. And that thing is almost impossible to lift, or at least not for me. I don't lift, bro. But what's really cool about meteorites, iron meteorites, is because of the immense heat and pressure that these things were under in order to create them. If you polish these stones, you see this pattern, which I'm not going to butcher the name. It is very German. It starts with a W. You can Google it. You can see this pattern of essentially formation of essentially faults within the rock as it was forming under tremendous pressure. Trans-Newtonian objects, or Neptunian objects, are primarily cometary in nature, and you can see from here the arrow is not pointing, or the arrow is pointing to the Trans-Newtonian object. The streak that you see that's passing through is an asteroid, but if you look closely enough, the object is slowly moving across the sky. If you looked at the distance between the Trans-Newtonian object, the thing that it's pointing at, and say that bright star in the bottom left, you'll notice that that distance actually decreases to a certain extent. Then we come to dwarf planets. Now, dwarf planets are, again, they are referred to as dwarf planets because while they orbit the sun, or star, in this case the sun, and they are spherical under their own weight and obviously do not burn hydrogen into helium, they are not sufficiently massive enough that they clear out their neighborhood. Ceres, it's smack dab in the center of the Milky Way, in the asteroid belt. Eris is a similar size to Pluto, or a little bit larger. Is pretty much in the inner part of the Kuiper belt, and Pluto is pretty much as well. There is enough Kuiper belt debris in orbit in Pluto's orbit that it is not classified as such. Now, Pluto was originally thought to be really boring until we actually sent a satellite to look at it. And what we found is that the geology of Pluto, and potentially the geology of dwarf planets beyond Pluto's orbits, are significantly varied. They are interesting. They are not just homogeneous ice balls. They have structure. They have plains. They have mountains, things of that nature. Things that we weren't quite expecting on the surfaces of these worlds. So they are much more geologically interesting, or geologically compelling, than we had originally thought. Ceres, on the other hand, is just kind of a big ball of rock. It looks very similar to it has very similar characteristics to the Moon and to Mercury. As I said, there are new information about Pluto. You have the Tomball Regio, which is primarily nitrogen ice, and then it's surrounded by water ice and water ice mountains. Again, it has a very thin nitrogen atmosphere. Previous to New Horizons, the telescope, the satellite that went out there and took this image, we really didn't expect the topography of Pluto to be all that varied. We kind of expected it to look similar to Ceres, where potentially, or possibly even Europa, where it was just an smooth, icy body. But nature is always surprising us. So let's talk about exoplanets. Exoplanets are, I think every astronomer has some interest in exoplanets, because obviously that's where we're going to find aliens. So what exactly is an exoplanet? An exoplanet, simply put, is a planet, as defined earlier, that is orbiting around another star other than the sun. So you have a planet that is, or an object that is spherical under its own weight, but doesn't burn hydrogen to helium through nuclear fusion in its core. And and exoplanets have been known since 1992. I think I went over this a little bit in lecture 1 or 2, where I talked about the scientific method and use exoplanets as my case study. And immediately, the first exoplanets that we found, nothing like we expected. The first exoplanets were around neutron stars, which again, once I go over a neutron star, you'll understand why that is so extraordinary, why we found planets and comets around pulsar, or around a neutron star or a pulsar. And then the first proper planets, or planets orbiting around stars very similar to the sun, were Jupiter-sized, but they were far, far closer to the host star than we see in our own solar system. And so it provided, so before, when we were talking about the model of a solar system, how it came into being, how it evolved and grew, we only had a single data point. We only had the solar system. And then when we found these other exoplanets, and we discovered that these other exoplanets were essentially nothing like our own solar system, that threw a monkey wrench in the whole thing. An interesting monkey wrench, but a monkey wrench nonetheless. Now, in terms of detecting exoplanets, because this lecture is getting a little longer than I anticipated, because I apparently just go off on tangents, I will simply just simply highlight the detection methods for exoplanets. It is my intention to make separate videos explaining the detection methods in a little bit more detail. So the first one that I'm going to talk about is called direct imaging. Direct imaging is where we take let me start off by saying that planets are, if you compared the brightness of a planet and the brightness of its host star, even if that planet is far away, you're talking about the contrast difference, or the brightness difference, between a flood lamp and a firefly. So the brightness of a star will just dwarf, or will wash out the light from any planets that are going around it. So how does direct imaging work? Very simply, we use techniques to block out the sunlight or the starlight from the host star, and then we're able to look at the environment surrounding it. And in some cases, we have found bright points that are actually orbiting around the star. And we've done analyses on it to determine that these are in fact planets and not, say, brown dwarfs or really tiny small stars. The interesting thing about these, or the monkey wrench that these supply to the equation, is these are Jupiter-sized planets that are hundreds of AU away from their host planet or host star. Again, to remind you, Jupiter and Saturn are 5 to 9 AU respectively. They are much closer to their host star than these directly imaging planets. And again, we really didn't expect to have planets forming that far out in the disk. Before we get into the next method, I want to just chat a little bit about center of mass. Now, in the lecture 5, I talk about the universal law of gravitation, and basically I make the claim that gravity results from two massive bodies. There is a force of attraction between them, and that force of attraction is causing what causes, say, the moon to orbit around the Earth. The point at which they orbit is called the center of mass. So the moon does not strictly orbit around the center of the Earth. It orbits around the center of mass, which is slightly offset from the center of Earth. and that offset is commensurate to the mass difference between the two. For example, if the masses were equal, then the center of mass would be directly between them. But because of the fact that we have this center of mass, that the center of mass exists, when you look at a host star and a planet, because of the gravitational attraction of the planet on the host star, it's going to make the star appear to wobble. So if you can use a detection method to detect this wobble, you can then back engineer that there is a planet of a certain mass located around it. And that technique, by Otto Struve, first developed by Otto Struve, is the radial velocity or Doppler effect method. And the way it works is through the Doppler effect. We look at the light of a star, and we will see that it periodically blue shifts, then red shifts, then blue shifts, then red shifts, and so forth and so on. And the amount of the red shift and blue shift indicates the mass of the orbiting body. And we plotted up something like this, where the amount of amount of shift, blue or red, corresponds to a certain velocity. And if you plot that up over time, you get this nice sine wave. Some of the positive values are when the planet or when the star is moving towards us. The negative values are when the star moves away from us. And for the first planet that was discovered around a solar-type star, that was 51 Pegasi b, and it has an orbit of around 4.2 days. Basically, due to you can do some math, and you can then deduce, because of the velocity shifts, the amplitude of the velocity, you can then determine the mass of the planet. And they did so with 51 Peg and realized that it was about half a Jupiter mass. The next detection method that I'm going to highlight is the transit method, which we do here at George Mason. Dr. Peter Plavchan heads a research group that uses our 32-inch telescope in order to confirm that there are planets which were initially detected by the TESS satellite, that these initial detections are in fact from a exoplanet and not some other astrophysical phenomenon. And the way that he does it, the way that Dr. Plavchan's group does it, is by looking at a star that we suspect there is a planet, and watching its brightness over time. And so, for the most part, you're going to, and creating what is known as a light curve. And so we have 4 different times. We have time 1, time 2, time 3, and time 4. And as you can see in time 1, 2, and 3, or 1, 2, and 4, the planet is off to one side from the star. But if the inclination is small enough, or is in line with our line of sight, then that planet is going to periodically move in front of the star, and it's going to diminish the amount of light that we see. The amount of light that is emanating from the planet is pretty much negligible in terms of the light of the star. Floodlight, firefly. So when the planet goes in front of the star, you're pretty much just blocking out the starlight from the sun, or from that particular star. And so if you can detect that dip, you can then determine something about the size of the planet, the exoplanet. Now there are various other methods. There's gravitational microlensing. There is astrometric detection. There is, why am I blanking on the? That is 5. Direct imaging, radial velocity, transit. Then the 2 that I'm really not really going to get into is microlensing and astrometric. So let's talk about the 2 workhorse methods. The two methods that have found the most exoplanets to date. That is the radial velocity method and the transit method. What can these find, and what information can we derive from what they find? Radial velocities are sensitive to large planets close in, because that, as I discussed with gravity is a function of mass and distance. The larger the mass, the larger the force, the larger the wobble. The smaller the distance, the larger the larger the force, the larger the distance. Yeah. The smaller, I almost had that. The smaller the distance, the larger the force, the bigger the wobble. So it's most sensitive to large mass planets orbiting at very close distances. At the moment, we are limited by technology in finding lower mass planets, like terrestrial planets, using the radial velocity method. Also, we are limited in a technological way of finding large mass planets further out. And the only reason for that is because of just lack of resources. Really, what you have to do is you have to be able to look at these systems for years in order to see if you can find an exoplanet out to that size, or out to that size. There are a couple other complications, but primarily it's time. As we know from Kepler's third law, the farther out the planet is, the longer its period is going to be. So, can we learn anything about the exoplanet's atmosphere from radial velocity? Simple answer is no. We can really only determine its mass from radial velocity. We can determine its orbital period and its mass and its distance from the radial velocity method. Transit methods are also biased towards large planets, and they are biased towards large planets going in. However, they are more capable of detecting smaller terrestrial planets. At the moment, we are detecting down to what we refer to as super-Earths. These are terrestrial planets which have masses that are 2 to 10 times the mass of the Earth. We have yet to really find an Earth analog, or the Earth 2.0, as they like to say. That is sort of the holy grail of exoplanet hunting at this point. Transit method also allows us to. Transit method also. I should also state that the radial velocity method gives you the mass of the planet. The transit method gives you the radius of the planet, and it also can tell you about the atmosphere. So, using a trick, using spectroscopy, essentially what happens is you can, by looking at the star's spectra, when the planet is in the way, with respect to when the planet is off to one side, there are going to be differences in that spectra due to the chemical abundances of the planet's atmosphere. So, for example, water, we don't expect water to be in the atmosphere of a star. However, water could exist, as it does on the Earth, in the atmosphere of the planet. So if this planet has a water atmosphere and it moves in front of the star, we now will see the spectra of the star as it is by itself, and then superimposed upon that, we will see the spectra of water and whatever other constituents that atmosphere has. So, win-win. Very cool. Right now, we have a tremendous amount of data about exoplanets, and my funnest fact about, and that is a word, my funnest fact about exoplanets is that every star that you see in the night sky, this is a statistical, we know this from basically statistics at this point. We haven't actually observed all of them. We've observed at the moment, we have clear evidence that there are roughly 4,600 exoplanets discovered. And then we have partial evidence of another 4,500. They are planetary candidates. They have not been fully confirmed yet. But through statistical analysis of those finds, we can confidently say that every star that you see in the sky either has or has had a planet or planetary system going around it. And given that there are hundreds of billions of stars in our galaxy, then there are, of course, are going to be hundreds of billions of planets within our own galaxy. And one of the interesting things, or one of the fun facts that we've learned from exoplanets, not only do we have to alter our view of how things get formed, but there may be planets out there that we don't see in our solar system. So if you can use the radial velocity method and the transit method on the same star, on the same exoplanet, then you get mass, you get radius, you get size. You take those two things together and bing, bang, boom, you get density. And the density of the planet gives you a very rough estimation of whether or not it is a rocky body, whether or not it is a gaseous body, and wait for it, whether or not it is a water body. So essentially, does the planet contain a large abundance of water to it? We refer to these as water worlds. And so instead of a rocky crust, you basically have a Kevin Costner world. You have a water shaped or covered world. We do not find these in the solar system, but they do seem to exist, and so it adds a fascinating element to solar system formation, or solar system, the variety of solar systems that may be out there. Now, what do planetary systems look like? I will make the caveat here that the planetary systems that we know of are biased by observational limitations. As I said, both the radial velocity method only really preferentially finds large planets close into their host stars. The direct imaging only finds big planets or massive planets way far out from the host star, and then transit methods can find small and large planets. But again, the orbital periods are small. But we can make certain assumptions or make certain claims about what other planetary systems look like, and they look weird. There are a few that look similar to our own solar system, 55 Cancri F. I actually know the guy who discovered that. So it looks very similar to the Earth, but a good number of them have very high inclinations relative to their host stars, and they have very high eccentricities, which again we don't see in our solar system in terms of planets, comets, comets, asteroids, sure, but not planets themselves. And there are even weirder things about these planetary systems, which I don't have time to get into. Why do these planets? Why basically do these solar systems look different than ours? Why do these massive planets appear to the transit? Why do these massive planets? Why are they so far out? More specifically, in this case, why are massive planets really close into their host star? And later on, we'll really get into the nitty-gritty of how a solar system forms. But the Cliff Notes version of it is that it forms from a large disk of material, and that disk of material is primarily composed of gas with a little tiny bit of dust, about 10%. And so you have these planetesimals that form within this disk, and they get large enough to become planetary size. But early on, there's still a lot of material, there's still a lot of gas, there's still a lot of dust and such, and there can be drag on that planet. And we refer to this as planetary migration. This is when the disk causes the planet's orbit to shrink, and so we believe that allows for these Jupiter-sized planets to be so close into their host star. And in fact, we believe we've seen evidence of stars that have eaten planets, that the planets actually migrated so far in that they got destroyed by their own stars. And in certain situations, you can actually have migration outward. Essentially, the dynamics between the disk and the planet are such that it actually makes the orbit larger. You also have something known as planet scattering, where here, instead of the gravitational influence or, say, the interaction between the planet and the disk causing the planet's orbit to change, you also have planet and planet interactions. If you have two planets or planetesimals getting too close to each other, the gravitational interaction between the two will literally sling one of the planets either way into the inner part of the solar system or way out of the part of the solar system, that explains that is what we believe explains the high eccentricities of the planets the exoplanets that we've seen. And in some cases, we actually believe that, yes, we actually believe that or models have shown that some of these planets could get ejected, and there have been at least two, to my knowledge, candidate rogue stars, and these are rogue planets. These are planetary size objects that are just passing through space, no longer bound to their host star. And so, at the moment, we have, like I said, thousands of planets to choose from, and they all are different in their own each individual ways. So far, we really haven't found one that's habitable. And I know I keep putting things off, but I will talk about the habitability of planets later on, probably closer to the end of the semester. There are a lot of different things, a lot of different factors that fall into what makes a planet habitable for life, but at the moment, we really haven't found any great candidates that fit the bill. There are a few that maybe kind of they fulfill one or two of the criteria that we have set forth that defines habitability, but they don't really match all of them. So we haven't quite, like I said, we haven't found Earth 2.0 yet. But that's, of course, assuming that life is like the life on the Earth. And as we've already found out, the solar system is not the mainstay, or at least there is significant evidence of solar systems that do not look anything like our own, and there are planets that we've never even seen yet. These water worlds. So who knows? As the eminent scientist Jeff Goldblum would say, life finds a way. So, with that, I will end this lecture, and I will bid you adieu. Peace out, and I will talk to you next time. And I believe we will be talking about. You know what? I'm not even going to lie to you. I have no idea what the next topic is. I believe we will be talking about formation mechanisms of the solar system, but I will also be talking about something else. And yeah, my memory is Swiss cheese. So anyway, I hope you enjoyed this. I hope you learned something. So again, peace out, and I'll see you next time.